We're now looking at forecasting. We're trying to understand the interrelationship between one piece of information and another. Now, with that in mind, we're simply trying to look at straight line relationships. And this means that we're effectively trying to interpret data in terms of a straight line on a graph. That being the case, we wish to express x and y. X being what we describe as the independent variable. And y being what we describe as the dependent variable. In simple terms, what we're looking at is this: by how much y will change in relation to x. Now, if we were to look at x and y, one classic thing that you would expect to see in any area of F2 is where x is some measure of activity, what I describe as L of A, or level of activity. In relation to y, well, it could be a whole host of different things, but often we're looking at cost. That's just an example. Please note that there are many other interrelationships that we could focus on. Of course, we could look at level of activity in relation to sales. However, we would expect that to be a relatively straightforward relationship. Or we could say that X was, for example, advertising cost in relation to Y, sales. So, given that we have a value for X, what we're attempting to do is to predict what the value will be for Y. Now, there are a number of ways that we can look at this. One technique we want to look at is something called the high-low method. Now, the high-low method is a very simplistic method where we just look at the high level of activity and the low level of activity and nothing in between. Now, this is quite important. You see, we're only going to look at two pairs of data, and if we've got two pairs of data, then we are easily able to describe a straight line relationship between the two. Before we go ahead and look at this in detail, let's just think about how this may look. Let's say we have a low level of activity and a high level of activity, and its corresponding cost. I suppose what we're doing is simply this. We're simply establishing a straight line relationship between the two, something like that. Now, if we're looking at high-low, it will give us some prediction. Having said that, it's not necessarily the best predictor. For example, we could have a whole host of other pairs of data that are not being considered. And I think we can all understand that the more pairs of data that we use within a prediction, the better it will be. The other thing you could argue is this. We're taking the absolute low and the absolute high. And in much data, you could argue that the extremes, the edges of the data, are less likely to be representative of the data itself. That in mind, let's just focus on the sort of thing that we may get and how we would deal with it. I don't think it's difficult, and I will tell you that high-low is almost guaranteed to come up a couple of times in your exam. What we have in front of us is an example, a typical example that you could easily get. The following cost information is available. We have output of 65,000 units and 105,000 units. Now, remember, when we look at high-low, to be pedantic about this, we have the high level of activity here and the low level of activity here. All we do is take that high and low and its corresponding cost. Very straightforward, the cost is given here. And the simple assumption is this. Any change between high and low level of activity will lead to a change in the cost. So the only reason for the cost changing is due to the level of activity and nothing else. If we make that assumption, it makes it very easy indeed to try and understand what the cost behaviours are, i.e. to separate the cost behaviours between a fixed element and a variable element. So let's just go straight ahead and see how we would go about this. If we were looking to calculate the variable cost per unit, one component of the cost, we can see that, well, if the only reason for the change in the cost is due to the change in the level of activity, all we would have to say is this. We take the cost at the high level of activity minus the cost at the low level of activity. Once we've established that the difference must be the variable cost, we're already sorted. We know the difference between those two is variable. And then we divide through by the difference in units, the high level of activity minus the low level of activity. And that will give us a cost on a per unit basis. Remember, when we look at cost behaviour, we expect the variable cost to be a constant on a per unit basis. Therefore, if we have our costs, 210,000 cost at the high level, minus 133,000 cost at the low level, divided through by the high level of activity, 105,000 units, minus the low level of activity, 65,000 units, and hey presto abracadabra, we can get our variable cost per unit. The difference in cost we see is 77,000. The difference in the level of activity is 40,000 units. 77,000 divided by 40,000 gives us 1.925 pounds per unit. So, we've established our variable cost per unit. Now, once we've got that far, it shouldn't be too difficult to establish the other component. If we're looking at our fixed cost, how are we going to establish that element? Well, in simple terms, we're going to say that the only two costs in the total cost are variable and fixed. So total cost equals fixed cost plus variable. Okay, all we have to do is some sophisticated algebra now. If we rearrange, couldn't we simply say that the fixed cost equals the total cost minus the variable cost? Now, for two levels of activity, we know the total cost, the high and the low. And we're able to calculate the variable cost at either of those. So using that, all we have to do is this. Let's just take it at the high level of activity. You don't have to, but let's just do it that way. Couldn't we simply say that the total cost is going to be 210,000? We know that already. Minus, at the high level of activity, the variable cost will be 1.925 multiplied by the level of activity of 105,000. Therefore, we establish a fixed cost which is £7,875. Now, if we can describe our costs in terms of fixed and variable, we can now use them from a forecasting perspective. All I've done here is separate into a variable and a fixed element. Let's go back to the information that we had in the question. We've used the data, but let's look at the requirement. Calculate the fixed and variable costs for the business, we've managed to do that, and the total cost for 165,000 units. Well, fantastic. We've got that for 165,000. All we have to do is this sort of thing. If we want the cost for a level of activity of 165,000 units, all we're going to say is this. The fixed cost is not going to change, 7875. Remember, the whole point about fixed cost is that it is fixed. It does not change. Whereas the variable cost is going to be, well, we said it was £1.925 per unit. We multiply that by the level of activity, 165,000. If we multiply 1.925 by 165, we get 317,625. We sum the two together and we get a total value of 325,500. And that is all we have to do. Classic high-low nonsense, this. Nothing more difficult than that. So, all you have to remember in recap is first of all how to deal with the variable cost per unit, and I don't think that's too difficult. And secondly, remember that sophisticated rearrangement. The fixed cost is simply total cost minus variable cost. Now, I've already said to you that with the high-low method, we're not doing a particularly good estimation. For those two basic reasons we said before. We're looking at the extremes and we're only taking two pairs of data when more than two pairs of data may be available. The other problem I have with the prediction that we've made, we're going to talk about a little bit more in the future. The reason why is this. If you remember the original levels of activity, we've got 105,000 and 65,000. And hold on a moment. What we're doing is we are predicting a level of activity of 165,000 units. Can you see a problem with what we've said here? Well, the problem I see is this. We know the cost behaviour to some degree of certainty for 65,000 and 105,000. But the value we've predicted, 165,000, is way higher than that. And of course, it's possible that both the fixed cost and the variable costs will change in some way at a much higher level of activity. We'll come back and discuss that particular issue when we look at the next topic. Now let's look at a more clever way of doing the forecasting. Remember, we've said that the problem with high-low is that we only consider two pairs of data. What we're going to look at now is something called regression analysis. Now, regression analysis, also known as least squares linear regression, is simply where, again, we attempt to try and establish the relationship between x and y, the relationship between two components, x the independent variable and y the dependent variable. Now what we could do is sort of remind you of what you did in the good old days at school. Do you remember at school you used to have some pairs of data that you would sketch onto your graph, or maybe even plot accurately? It's possibly a better way of describing it. And what we want to do is, by eye, come up with a line of best fit. Something like that. Now, all well and good. It sort of works. The only reason why I suggest that is that what we're attempting to do here is exactly the same sort of thing. We're attempting to estimate the relationship between x and y, given that we have a number of pairs of data. But we're going to estimate using estimating formulae. And please note that these estimating formulae are given to us in the tables that the examiner gives to us. That being the case, let's just have a look at the estimating formulae themselves. The estimating formulae gives us a value for B and a value for A. B. n multiplied by the sum of xy minus the sum of x multiplied by the sum of y divided through by n multiplied by the sum of x squared minus the sum of x all squared. And then likewise for a. Now these look rather complicated, but what we're going to find is that they are not too difficult to deal with at all. So what does this b value and what does this a value mean? If we know those, we have an understanding of what we are attempting to achieve. If I just tidy up what we have here and just draw in the line of best fit that we are attempting to achieve, let's say it's something like that. All we need to describe this straight line is to describe two components. First of all, we want to describe the intersect with the y-axis, and this is called A. Secondly, we want to describe the gradient of the line, the amount by which y changes for a change in x, and this is called B. If we know these two components, then we are able to describe the relationship in the form y equals a plus bx. So just thinking back to the high-low example that we talked about before, A is simply going to be the fixed cost, the element that does not change with the level of activity, and B is going to be the variable cost per unit. And you can see it's per unit because we have to multiply by the number of units the value of x. So that's what we're attempting to do here, and I've just illustrated A and B in terms of level of activity and costs because that's what we saw before. But of course A and B could describe many other relationships between the independent variable x and the dependent variable y. Now, if that's what we're trying to do, let's get back to the formulae themselves. They look really rather complicated. But the key with these formulae is to get some critical data out that we can then play with. In simple terms, the data that we want is the sum of x, the sum of y, the sum of xy, the sum of x squared, and although we don't need it with these two formulae, it is possible that we will need the sum of y squared in a moment. If you just notice, the sum of x is already represented here and also here. The sum of y is represented here, the sum of xy here, and the sum of x squared here. So, if we have these values, we're able to quite easily come up with a value for b. Now, let's see how we get those numbers. I'm inclined to say that the next part that we're going to look at is for information more than anything else. But I think it's critical that we have an understanding of what it is that we are attempting to do before we look at the sort of things that you may be required to do in the exam. We have an example in front of us. In the example, we have 6 months from January through June. And then we have values of units and cost. Now when we look at these, I'm looking at the units to be our x value. They will be, if you wish, the independent variable, and the cost to be our y value. My suggestion is that cost changes with the number of units rather than the units changing with the value of cost. That being the case, well, I'll tell you what we could do. First of all, we could just consider how the high-low method works with this, just to reinforce what we did a little while back. If we're looking at the high-low method, remember, what we want are the high and the low levels of activity. If we're looking at the high level of activity, the highest level of activity is 900 units, and the low level of activity, 400 units. Notice we look at the levels of activity rather than the cost. Once we've got the high and the low, then we will link in the associated costs. So before we go any further, should we just play around with those and see how high-low will get us an answer? I've said to you, first of all, I want a variable cost per unit. And to get the variable cost per unit, remember the assumption when we look at high-low is that any change in cost is due to a change in the level of activity. What I mean by that is that any change in cost must be a variable cost. What is the cost at the high level of activity? Well, the cost at the high level was 2,300 and the cost at the low level was 1,050. So the difference between the two, of course, is variable. The high level of activity was 900 units and the low level of activity was 400 units. So in simple terms, we're seeing that the cost is changing by £1,250 whilst the level of activity is changing by 500 units. Hey presto abracadabra, we see that the variable cost per unit is £2.50. Not too difficult. Once we've got there, all we have to do is to pump those numbers back in to establish the fixed cost. If we're looking at the fixed cost, what we typically do is to look at the fixed cost at the high level of activity. Of course, it doesn't matter whether we use the high or the low, but invariably when I ask students, they always go for high. Don't ask me why. Therefore, if we're looking at the fixed cost, the total cost is 2,300 minus the variable cost. Well, we said that the variable cost per unit was 2.5. And we said that the high level of activity was 900 units. 900 multiplied by 2.5 comes to, very simply, £50. £50 if you wish in total. So, what we've been able to do here is to separate fixed from variable, and hence we are now able to forecast. If we want the forecast at 850 units, all we would say is that we have the fixed element, £50, plus 850 units, each at £2.5 per unit, and that will give us the total of 2,175. So, using this information, that is how we would use the high-low method. Now let's get back to the plot. Remember, we're looking now at regression analysis. And I said I wanted the sum of x, the sum of y, the sum of xy, the sum of x squared, and so on. That being the case, what we could do is prepare this sort of analysis. As I've described to you already, the units are the independent variable and the costs are the dependent variable. The units relate to x and the costs relate to y. Oh, before we go any further, there was one element of our formulae that we didn't talk about. N is simply the number of pairs of data. If you think about it, we've got 6 months of data here, therefore n equals 6. Nice, easy one to deal with there. So, all we need to do is to get all those summed values that we were talking about. So we want the sum of x and the sum of y. We simply need to add them up, nothing more. If you were to sum x, what do we have? 400 plus 600 and so on. If you check through these numbers, I think you will find it comes to 4,000. The sum of y, we just want to add up. Each of these comes to something like 10,750. So let's look at summing x multiplied by y. First of all, let's multiply x by y. If we multiply 400 by 1,050, we get 420,000. We multiply 600 by 1,700, 1,020,000. We multiplied 550 by 1,600, 880,000. 800 by 2,100, 1,680,000. 750 multiplied by 2,000, 1,500,000. And 900 multiplied by 2,300, 2,070,000. If we add x and y, we get the sum of xy. The sum of xy is 7570. Then we look at squaring x. Remember, we needed the sum of x squared somewhere. So if we're looking at the square of 400, we get 160,000. Of 600, 360,000. Of 550, 302,500. Of 800, 640,000. Of 750, 562,500. And of 900, 810,000. If we sum all those together, we get 2,835,000. Now, I will say that if we were just looking at the value for A or the value for B, that's all we need. But as I said before, it's possible that we will need the sum of y squared later on. And so it makes sense for us to do that now. I think we can all square these numbers. So I'm simply going to tell you that it comes to 20,252,500. So we have some of the numbers that we need. Now, why am I not too excited about doing this bit of the analysis? Well, the answer is this. Given that your questions are going to be 2 markers, is your examiner going to get you to do this? I suppose theoretically, yes, but in practice, I'm inclined to say never. From that perspective, I'm expecting your examiner to give you this information. You will simply be given the sum of x and the sum of y and the sum of xy and so on. All you need to do is to be able to take this information and slot it into the formula. That's it. Nothing more. So given that you have this sort of information, let's now look at calculating B. Now, I don't know about this. Normally I would always advise you to write down the formula before you use it. But it is going to sit there in front of you. You have it in your question pack. And also, you've got very limited time. So just make sure that whatever you do, you write down the information correctly. If we're looking at B, I'm going to write out the formula just to make sure that you are looking at it at the same time as we're talking about it. N, the sum of xy, minus the sum of x multiplied by the sum of y, divided through by n multiplied by the sum of x squared minus the sum of x all squared. So that's what you're trying to do. So we slot the numbers in. N, 6, multiplied by the sum of xy, 7570 thousands, minus the sum of x, 4,000, multiplied by the sum of y, 10,750. We divide through by n, 6 multiplied by the sum of x squared, 2,835,000, minus the sum of x, 4,000, all squared. Now, please note, if you're going to do this sort of thing, you must have a scientific calculator. If you have a modern scientific calculator, and what I mean by that is any normal calculator that has been made in the last 5, even 10 years, it has what I would describe as computer logic. And all that means is that if you pump the numbers in the correct format, the calculator will do the work for you. If you have a simple desktop calculator that is not scientific, you've got to be a little bit more careful as to how you put the numbers in. Make sure that you have a go at this and satisfy yourself that you can get the right number. It's not difficult, but let's make sure we get it right in the exam. So we pump the numbers in, and what we end up with is 2.396. So there's our value for B. What does that mean? Well, if you remember, we were looking at X in relation to Y, units in relation to cost. And B is the element that changes with each unit. So before we go any further, we could say something like this, i.e., the variable cost per unit is £2.396. That's what we're describing, the variable element. Once we've got the variable element, then we can establish what the fixed element is. If we look at A, well, remember, we've got our B factor. We needed that first of all. Now we can look at A. A is where we take Y divided by N minus BX divided by N. Well, okay, if we're looking at this, let's just make sure we got it the right way around. The sum of Y divided by N minus B, the sum of X divided by N. If that's the case, we simply drop the numbers straight in. The sum of Y was 10,750 divided by N6 minus, didn't we say 2.396 was the value for B? Multiplied by the sum of X, 4,000, divided by 6. Now, I don't know about you, but you may see that there is a strong similarity between what we've done here and the high-low method. Effectively, we're doing that full cost minus the variable cost per unit idea. If you see it, all well and good. If you don't, it doesn't matter at all. And we establish a value for A of 194.33. i.e., what does that mean in this case? Well, I suppose it means the fixed cost in total is £194.33. Now, once we've got that far, well, what can we do with it? Well, the issue about regression is, yes, we may be asked to do this, but there are a number of things that we may be required to do with this value.